Oh, we're drinking Pacific. My God, you messing me up now.
The thing with the quote?
Yeah, we do.
She gave us a quote?
Yeah.
I hate the quote.
Thank you for staying. I'm sorry that
I stayed because I'm
I'm sorry that I'm always so late. Works out though, I guess, right? I mean,
change your ways for me.
I left my folder, my pencil, the thing.
all right, can you guys clear your desks? We have, so I'm going to collect the ecology stuff, but I also have to give you the pre-test for the chemistry stuff. Remember I told you about that? So, it's not, don't stress about it because it's just, to measure, but you should try your best. It's on a Scantron, but unfortunately I don't have any Scantrons. Do you have any Scantrons by any chance? Would you mind if I went? Okay. I'll be right back. I'll leave some in the desk.
Okay.
I'm sorry, I can't. Yeah, I know. It's on the folder. Yeah. Okay, well, I'll be going to go semester, so.
She was. She got everything. Her lowest grade is 92. Wait, what? She goes, I'm so good. I'm getting myself the lowest grade.
The only reason I stopped studying that one was because I got 9 Okay, well, you're smart. When you just not study. I'm very extra study. I don't study. I have a couple of courses. Oh my God. Oh, I have them on every week. I didn't say last year.
All right, who wants to help me? Could you go and collect all the ecology quizzes? Thank you. And who else wants to help me? I obviously need a lot of help today. Omar, can you come distribute these Scantrons? Thank you very much. Is everything okay? Arsh, you're doing that for me? All right.
Do you listen to Strobo Scandal? Oh, yes, politics. Oh, it's your favorite subject.
Politics? Huh?
He loves politics.
Does he really?
Yeah, and he always does.
You do too?
I don't like them. They stress me out. I don't like people arguing. I don't like talking to them. Yeah, it's just not a thing.
Yeah, if you want to remain in people's good favor and you sort of know that they're not in the same boat as you, then yeah, just avoid it.
So, the girl that's like the gun girl from Penn State.
Where'd you guys test?
The what?
Her name's like Caitlin Bennett.
Uh-huh.
I think she's so funny how she thinks like her mentality is just going around to colleges and insulting people and then not having anyone like fight her or anything because she can't carry.
She carries a gun, yeah.
I just think it's so funny.
Well, that's just one word for it. Thank you very much. All right. So you guys, I'm going to give you this quiz. I'd actually like you to get in like somewhat quiz positions. You guys know what that means, right? Let's go. Let's just to. So you should you guys can maybe stay like this. Maybe Sarah, you could go over here. Yeah, you can maybe come over here too. Wait, no, not Anna. Anna. No, you and maybe one of you guys can move back there. And then maybe the other one of you could go. I don't know, whatever you guys want. Make sure you're not like right next to someone who. Alright. So you guys have, I'll give you 20 minutes to do it. There's 32 questions. I don't really want to waste that much time on it. I don't think that, many people will know that many of the questions. So feel free to answer, I don't know, or whatever. I'm not sure. Right? You can write on the paper. You can write on the scan time. There we go. All right. So we are now. What's the date? I'm sorry. Today's the 7th, 18th? 18th. Okay. Here. Did you get one? No, not yet. Did you get a haircut?
Yeah.
Nice.
I don't like it.
You don't? I like it.
For something.
Chemistry. Read that. Olivia?
What's the one? The test.
You guys have giggles all the time in this class.
Yeah, because I was going to
Try your best, but again, and I'm going to put this in the grade book, but I won't count it as for a grade, obviously, right? That would be mean. You didn't learn this?
The 18th.
However, today's the 18th. In a few months after we've done like all of our chemistry stuff, you'll see this same exact quiz. So, and then it will count. So just take what information you will with that. You guys will know all this stuff by then.
do this. I seriously don't know.
Then just put, that's why I'm only giving you 20 minutes. I mean, some people who really, some of it you might know. So just answer ease if you don't know, or just like blindly like do a pattern. But you do still have to take it. Do you think 17% will get us through class today? 17% on my thing?
Do you want to borrow my charger?
Do you have one?
Yeah.
Oh my god.
Okay, I'm sorry.
Alright, no, we don't need to clap, but we are very grateful to Arsh, but we don't need to clap.
Welcome.
Thank you.
Welcome.
I'll charge it now and then I'll give it back to you. Remind me to give it back to you.
Yeah, that was
I just forget. value any of this. Okay. Is anyone else really demoralized? No. The point is not to. All right. That's okay. That's the idea. It will make me look really good when you guys know something after it. Right? That's the point.
Yeah, same.
Please don't do that. Then they'll be like, what are you teaching them? You guys can have like 5 more minutes. I think that's enough, right? Bless you. All right, is everyone done?
I'm just playing at the ease.
Who's not?
All of them are these.
Really, can we try for this one? No, it doesn't actually.
Yes. Can you what? Yeah, go ahead. Yeah. Are you okay? Or was it not too bad?
3 for a while.
I knew 10.
Are you serious?
Okay, so you guys should remember the questions on here.
I'm going to memorize.
And you'll know. I don't want you to memorize them because that's really testing you. But, just be aware that these are the types of questions you will be able to answer by the end of the meeting.
They don't teach science.
Okay. That'll make me look really good. Is it funny?
Well, I mean, if I don't know after learning it, then it's bad.
Yeah. But if you just don't know it, then that's fine.
Too big on mine.
Yeah, so today we're taking notes and we're starting chemistry. So we're going to start kind of tackling this stuff that you guys apparently didn't feel like you knew, but alright, so these are here on the table so that I get some recognition of this.
We're supposed to learn that. They didn't teach us.
I think I did a little bit of that in nature.
Oh my gosh, I don't know what we did in nature.
Sick.
I'm going to memorize a song tonight, and then I'm going to sing it tomorrow. You guys got to do it.
Holy George.
Are you serious? I need to have proof that you had it, or I'll send a picture. I know.
You guys all got one, right? Periodic table song?
Yeah.
There is, and I'm going to play it for you guys right now. Do you guys want to hear it? Just to kind of loosen us all up after the long weekend. All right. All right. Are you guys ready to start? So I want you guys to have your notes out. I want you to be ready to take notes. Some of this chemistry stuff is kind of hard to just get your mind into, and some of it we're just gonna glaze over because we can't get into the really nitty gritty of it. You guys will have chemistry next year, and you'll have it senior year. So you can work out all the kinks with Mrs. Riley and Mrs. Reel. But we're just doing brief overview for the stuff that we need to know that we can, so we can talk about things in the way that I want to talk about them, right? Just to be a decent general science overview, right? But I'll play you the song because it's kind of
I'm starting already.
you know it by heart.
I know the first two by heart.
I know the first two.
I lost the paper.
I know all of them.
All right, so All right.
Carbon? No. Hydrogen, oxygen, no. Hydrogen, helium, alright.
Hydrogen, helium.
Lithium,
Do we
bromine.
have to know all of them at one point?
You're not going to have to memorize all the things in this class. Eventually, you'll have to know. I do want you to know some of the basic symbols, and like you know the ones that we're going to use every day. For example, like carbon, huge. You have to know what carbon is, and then like that you have to know it's C. But you don't have to memorize like all the different ones. But I will give you a list of ones that I do kind of want you to know, right? And just like distinguish, like sodium. You should know what sodium is, right? Na. You should know what nitrogen is. All right, so today, main thing, we're going to define the important terms of chemistry, right? We're going to familiarize ourselves with the periodic table. That's like the main thing, how to read it and like what it has in it. And just like marvel at how beautiful it is. It's really like quite a work of art. So I know it sounds really cheesy, but it's like if you had discovered it, like you would feel, I mean, not that I have discovered it, but like, I don't know, it's like beautiful.
You're proud of it.
Okay, so first of all, I want you to answer this question. What's matter? So chemistry is like about matter, right? Charlie?
It's what everything is made up of.
What makes up, something that takes up mass, right? And takes up space and has mass, right? Everything is made up of some type of matter. Everything known to us, right? And how many different types of matter are there if we were going to classify them into different groups? Arya? 3. Who says 3?
4.
Actually, there's plasma.
All right, so we're to get really technical. All right, no, it's 4 states, right? So it's solid, right? Solid, liquid, gas, and then plasma, right? Have you guys heard of plasma before?
Yeah.
All right, so we're not going to talk about plasma in this class ever, except for just now and just like mentioning it as the 4th state of matter. Some things that I've read have like 5 or 6. Yeah, they're.
Like if you include colloids like shaving cream or like gel.
We're not going to include those though,
TV,
but
those
nice.
Plasma TVs.
Yeah.
Yes, Mike.
Yeah. All right. So, okay. So what is matter? So these are the different states of matter. Okay. What's this? Periodic table of the elements, right? What's an element?
It's like earth, water.
It's like the purest substance in the earth.
Right. It's a pure substance in earth that cannot be broken down into another type of substance by normal chemical means. So it's a substance, a pure substance that can't be broken down into another substance by normal chemical means. So it's basically the most, like a fundamental type of substance, right?
I know the diatomic elements. I only know the diatomic elements because like I was forced to learn them for a test.
All right, that's fine. You're gonna have to know. I want you guys to know, like, kind of, like, all of these up here. But all right. So first of all, how many elements are there on the periodic table? There are 118 known elements, right? Are they all gases, all liquids, all solids? It's a mix, right? So they're all different types of states of matter here, right? And then some of these, like these later ones, they're all like actually man-made. They don't occur naturally on Earth, right? But they've been discovered, right? So we have a nice 18. It's nice because it actually like rounds out the table. Because before these 4 were discovered, it was like, it looked kind of ugly, right? So anyway, so this is the periodic table, right? And I'll play you the periodic table song because this is how we're going to organize all our little elements. So let's see if I can do that and show. And this song is so cheesy and like it's not really going to help you that much, but.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium and lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon, phosphorus, then sulfur, fluorine, and argon, potassium, and calcium, so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable, halogens and alkali react aggressively. Each period will see new outer shell, electrons are added, moving to the right. Iron is the 26th, and cobalt, nickel coins again, copper, zinc, gallium, germanium, and arsenic, selenium, and rhodium, krypton, half-light, silver, rubidium, strontium, and yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silverware, then cadmium and indium, tin can, antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table split. Well, atoms have just begun. Platinum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, terbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, barium, and lead is made for your tummy, polonium, acetine, vanadium, radon, lithium will last a little time, radium, then actinide and 89. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shell, electrons are to the right. Actinium, thorium, protactinium,
Just kind of gave up now, I think.
plutonium, americium, curium, berkelium, californium, titanium, rhodium, nobelium, nobelium, lawrencium, rutherfordium, lithium, silicium, borium, lithium, mechnurium, reptilium, mercurium, copernicium, nihonium, ferrovium, moscovium, livermorium, tennessine, and organesson, and then we're done.
Yeah, they're just like, let's just read them all now. Do you guys know what song that is?
The periodic table song 2018.
What, do you know what the tune is? The tune?
Oh, I know what it's like. Oh, yeah. Classic.
The can. It's that, like, you know, where they like do that, like, kind of like.
Can we do that? The rock cat?
Now you guys can make a project where you'd know. I'm just kidding. What's going on? But isn't it cool how, like, I mean, it looks like it was made on a whiteboard, right? But then, like, some of them, like, they actually, like, have it, like, you know, the mercury was moving, and, like, you know, like where they draw on the muscles for, like, this. Anyway, I think that is pretty fantastic. But yeah. Anyway, kind of interesting, right? Okay. Hang on, I have to do one thing. All right, so just take a look at the periodic table for a second. Try to familiarize with some of some of the symbols and some of the like so the symbols, and notice like what the format of the symbols is. And while I try to do this.
It's the it's the number of electrons, right? And you have like the shell and there's like 2 different more than 8, right?
Have you seen like the Chem say it's like you could say wait, is there where it's like where it's just same with Chem?
Oh yeah.
Are you top on titanium and
Oh yeah.
you don't talk about
Oh yeah. Oh yeah, I made one.
All right. Shh. All right, we're ready? Okay. So an element it's a substance that can't be broken down to a simpler substance by normal chemical means. We just talked about that, right? So we said that there are 118, right? Look at the chemical symbols. What do you notice? So what's the maximum number of letters that they have? Arsh. 2, right? And what's this, like, in terms of capitalization, what's the rule? You only capitalize the first one, right? So sometimes I see students do this, like when they're talking about sodium, I see them do this, and it really, like, bothers me because you can't do two capitals next to each other, right? So make sure when you do something, it's always going to be capital and then lowercase for the second one, right? Question? Did you say no? All right. So make sure you keep to those like what's it called? Like standards, those conventions, right? So it's one or two letters. Well, only the first one is capitalized. Are all of them intuitive? No, right? So hydrogen H, we're fine, right? Helium He, that's, you see why they do He, right? Lithium, beryllium, we're all good for most of this, but like, so I want you guys to keep, we're not going to go too much in this area, but I want you to keep in mind, carbon and calcium both start with what? C and Ca, right? But Ca is calcium, C is carbon, right? Oxygen's pretty self-explanatory. N is nitrogen, right? But one that's weird is the Na is what? Sodium. I think in England maybe they still call it natrium. So I think that's where it came from, the Na. It's not just like random, like let's confuse chemistry students. It was actually based on something. But remember, so Na is sodium, right? What about S? So if I say what's sodium, don't say S. What's S? Sulfur, okay. What about Se? What's Se? Selenium, right? Selenium is right there, right here. All right. What about Si? Silicon, right? What's silver? Thank you, right? Where is it? Silver, right? So don't get mixed up with Si and silver, right? So Ag is silver. What about gold? What's gold? Au. Au? Okay, good. Who said Fe? What's iron?
I was excited for iron. I thought you said iron.
So iron, gold is Au. So here's silver and gold. Iron is Au, right? Oh, sorry. Oh, gold is Ag, Au. Iron is Fe. Excuse me. Mercury. What's mercury? That's another weird one. Not M, not MC. Hg, right? That's another weird one. So just like keep in mind these weird ones. Copper. What's copper? Cu, right? What's Co then? Cobalt, right? So just be careful of these like little ones, right? I want you to know, like be pretty confident of like 1 through 20, let's say, right? Make sure you know all the symbols. And then other random like potentially confusable ones like cobalt and copper, and then like silver, gold, mercury. Yeah. I think those are the main ones that I want you guys to know. Okay? So we're okay for this? So yeah, beware of tricky ones. All right. So an element is something, it's a substance that can't be broken down into a more simple substance by normal chemical means, but still that means that elements are made of something. What are they made of? What's the smallest unit of element? Arsh?
Like a single molecule, a single atom of it.
An atom, right? Is that what you guys are all going to say? Yeah? All right, what are the parts of an atom? So an atom, first of all, is like the basic unit of matter, right? That's like the most fundamental thing, the most fundamental form of matter. Arya? You, what the parts of an atom are? Awesome, good. So an atom itself can be broken down into protons, neutrons, and electrons, right? Proton, and they all have their own associated charge, right? Pro means positive, right? Okay. Neutrons means not negative. You just said it. Neutral means neutrons means neutral, and then electrons means negative, right? Okay. So we're all good with this? You know this. Review. Did anyone not know this part? Okay, you guys knew that, right? Okay. Can I keep going or no?
Can you go back for 2 seconds? I'm sorry.
Okay. So if I want a neutrally charged atom, what has to equal what? Bro? Protons has to equal electrons, right? Is the neutrons going to change the charge at all? No, right? So 1 for 1. If I have one proton, I have 1 electron, they're going to cancel each other out, right? But if I have more protons than electrons, then I'm going to be what charge? Positively charged. And if I have more electrons than protons, then I'll be negatively charged. Okay. So in a neutral atom, the number of protons and electrons are equal, right? All right. So people have been like studying atoms for years or chemistry for years, and so this one guy, Niels Bohr, came up with the Bohr model for electrons, right? The Bohr model for atoms, right? So basically he did it in this orientation. He said that this center part is called the nucleus, right? And it contains protons, which are the yellow balls, right, which are positively charged, and those orange things, which are supposed to be representing neutrons, because they have no charge on them, right? So the nucleus is contained of neutrons and protons, and then the electrons are sort of like traveling around in these concentric circles. That's what they were saying. And so do you see how the electrons are in that picture? Right? What's the relative size of like a proton and a neutron versus an electron, like as depicted in this picture? And like all models aren't always to scale, but if this were to scale, let's say, what's the relative sizes, Lita? Electrons are a lot smaller, right? So good. And so these are basically, electrons are traveling around the nucleus at like some sort of radius, at some sort of distance, and they can only go in these certain like energy levels. So each of those like circles is called an energy level or an electron shell, right? And so you're filling up the electrons into those shells, and they're basically traveling around the nucleus. And what prevents the electrons from just like flying away and going like off into some other place?
Their electric charge keeps them filling the protons.
Good. So opposite charges attract each other, so they're kind of still attracted to the nucleus, so they're going to stay around because they want to be attracted to that. Perfect. Okay, good. Do you guys know what the outermost shell, electron shell, is called?
The valence electrons.
Good. Did everyone hear that? So these are like, some of them will have like 1, 2, 3, 4, 5. They'll have many subsequent shells which can house all these electrons. But the outermost one of any given one, and for some of them, the outermost one might be the second one. They might only have that one shell. But other ones might have like 4 shells, right? But in any case, the outermost one is the one that is doing the reacting with other stuff. So that's really the only one we care about. And that one's called the valence shell. And the electrons in that shell would be called what? The valence electrons, right? Okay. We're good? Okay, did I lose anyone? All right. Is this in reality the way things work? No. In reality, and we're not going to get into it, there are these like orbitals, and then electrons are not really ever, we can't predict where they're ever going to be. So there's like this probability ratio. We're not going to talk about that. But the current model that's being favored is that electrons are sort of like in this big electron cloud floating around the nucleus, right? So that's like the modern theory of it, right? But still, the Bohr model, is it totally useless? Should we just like throw it away and like be gone with it? No, why? George?
It kind of still shows like the basic ideas, like how they're kind of close to each other.
Yeah, it's like a neat way of sort of seeing how they're like distributed, and then how they might like to predict. It does help predict how they are going to react with other substances and stuff, right? So it's still useful even though it's not completely accurate, right? All right. So let's talk about protons first, right? And let's look at the periodic table, right? The number, if you notice how the periodic table is organized, you see it's like it increases from left to right, and then it increases as you go down, right? And it's in like they're in consecutive order, right? So it's like 1, 2, 3, 4, 5. Do you see those numbers in the like upper left corner of this periodic table? Right? In different periodic tables that you see, it might be in like a slightly different location, but you should recognize that number. You should be able to see that number is increasing, and that's called the atomic number. Does anyone know what that represents?
The number of neutrons traveling around the nucleus.
Close. Not always. It's the number of protons in the nucleus, right? And often the number of protons and the number of neutrons is the same, but sometimes it's not. So we can't always say neutrons. So the number of the atomic number is the number of protons in the atom, right? So if I say, and you guys should keep these periodic tables handy because I'm going to ask you questions on that. So for example, let's see, like Jasmine, iron. How many protons are there in iron? 26, right? George, how many are in nitrogen?
7.
Good. How many are, Hannah, how many are in sodium? Sodium's hard to find. That was a tricky one, so. Na?
NA.
How many,
11.
11, good. All right, Mike, how many protons are in lithium?
One.
Okay, no?
Oh. 6. Oh, I thought that was the number in the table.
No, so the number on the upper left corner, that's what we're doing. That's called the atomic number, but that also is the number of protons. So if I say, like, the atomic number is 14, how many protons are in that? You would say 14, right? So lithium is 3 on the periodic table, so it's 3 protons, right?
One's like over 100 protons.
Yeah. Like Afghanistan is, has 118. All right, we're good? All right, so...
I just didn't think that was possible. That's why I didn't say it like that, no.
No, you can, yeah. So that's why it's like so beautiful that you can find all these elements that have like exactly one more number of protons in them and then line them up in this chart. Like that's part of like the beauty of the periodic table. All right. So basically it also identifies the element. So if I say I have an element that has 44 protons in its nucleus, what would you immediately know about it? It's ruthenium, right? So like the atomic number immediately is the name of the element is the number of protons, right? You can't change it. Right? If I say I have another element with another number of protons, can it be the same element as the one I said before with a different number of protons? No. So if you change the atomic number, basically you change the element. Like end of story, right? Okay. Why do I have the periodic table here again? I'm not really sure. Okay, so we're going to continue, right? Now we're going to go on to the next subatomic particle, which is in the nucleus, which is called neutrons, right? Neutrons, again, what kind of charge do they have? Neutral charge, no charge, right? And so basically you never are just given the number of neutrons. I never will say like, okay, here I have 5 neutrons, right? I'm not going to say that. What they do give you though is this thing called a mass number. And the mass number is the number of protons and the number of neutrons in the atom, right? So how could you deduce the number of neutrons if you're given the mass number? George?
You could subtract the atomic number from the mass number.
Good, exactly. So if I say, okay, I have an element that has, let's go back here, and you guys can look at this one if you want. If you say, okay, I have an element that has 36, the mass number is 36, and its atomic number is 17. Tell me the element and tell me the number of neutrons. I want everyone to think about it first. So what did I say? The mass number is 36, right? The atomic number is 17, right? Is everyone thinking about it? Do you have it? Mary, what element is it? Chlorine, good. And then what's the number of neutrons in it? Addie? 19, right? Because you subtracted 17 from 36, right? Right? That makes 19? Good. All right, good. George?
But it says 35.453. How would you have 1 point, or how would you have 0.5?
That's not the mass number. So here's, thank you. This is leading into my next point. So mass number is the number of protons and neutrons in an atom. Can I have a half a neutron? No, right? So what does the mass number always have to be? It has to be a whole number, right? So is this number on here the mass number then? No. Can the number of neutrons change and still have the same element? Yes. So I could have chlorine that has 17 protons and 19 neutrons, or I could have chlorine that has 17 neutrons and 17 protons and 20 neutrons, right? I can change the number of neutrons, still chlorine, right? Because what's not changing?
The protons.
The number of protons or the atomic number, right? Okay. So you guys are good with this, right? Okay. So the mass number, it's not indicated on the periodic table. So don't look for the mass number on the periodic table. It'll always be given to you, either at the end of the element's name, or I'll just say the mass number is 16, or the mass number is 50 or something, right? I always give that to you, okay? Do you guys know what the word isotope means? Arsh?
No electrons?
Hmm?
What has no neutrons?
Not exactly. Does anyone have any idea? Other than ours? So basically, an isotope is a different version of the same element, but with a different number of what? Neutrons. So before, remember I had, what did I have? I had chlorine. I said I had chlorine 30, and I had
36.
So chlorine is 17, right? So I had 17 protons in here, right? 17 protons. And then I had, but it was chlorine 36, right? So I had 19 neutrons, right? So suppose I have chlorine 35, right? That means how many protons do I have? Always the same, 17. That should have been like really quick, right? 17 protons, and how many neutrons am I going to have in this one then?
18.
Yeah, 18, right?
Neutrons, yeah,
Good? Right, so these two in relation to each other are called isotopes. Right? So this is one isotope of chlorine, this is another isotope of chlorine. Are we good for that? Yeah? Okay. And so what's the mass number of what? No. All right. It's pretty clear, right? When you put the dash and you put the number after it, that number refers to the mass number. So chlorine 36 is the mass number, right? Chlorine 35 is the mass number, right? So I can figure out the number of neutrons if I'm given the name of an element, right? Okay, we're good here? All right, so this is like probably just like overkill, but so element name dash mass number. For example, carbon 14, nitrogen 15. So I want you guys, for these three isotopes of carbon, right, I want you to tell me the number of protons and the number of neutrons, right? Try that on your own real quick. All right, write it down. I'm going to come around and look, see if you're with me or not. How do I find the number of, so how do I find the number of protons if I can give a carbon 12? Number of protons. Number of protons? What's the number of protons? We look at the atomic number. Where's the atomic number? Okay, so what element are we talking about? Okay. Carbon. I'm doing carbon. So carbon is what? Okay, so that means 6 means what? That's the atomic number, which means that's the number of what? Good. So we have 6 protons. How many neutrons are we going to get in carbon 12 then? So 12 is the mass number, meaning the number of protons and neutrons together. Okay, what about carbon 13 then? Got it? Alright, are we good? Did you guys all get answers? Okay. So for the number of proteins for carbon 12, how do we know it's 6? Because of what? Because carbon is, the atomic number is always 6, so it's always going to be 6 for all three of them, right? No matter what? We're good? Alright, so how do we get the number of neutrons for carbon 12? 12 is what again? What number is 12? The mass number, so you subtract the atomic number from the mass number to get the number of neutrons, which is going to be 6. What about for the next one? 7. What about for the next one? 8. Right? So if I gave you two isotopes and I told you the atomic number, or I told you the name of the element, and I gave you a mass number, you'd be able to figure out the number of neutrons, right? It's like basic math, but it's pretty, you have to use this to your advantage, okay? Okay, are you ready for more terms?
Yes.
Okay, and we were kind of getting to this. George, this is where your question came in. So atomic weight or atomic mass, and this term is used interchangeably, that is basically, it's the decimal number on your periodic table, all right? And what does that mean? Because you said you can't have half of a neutron or half of a proton, right? So that means it's basically the average of all the mass numbers of all the isotopes on Earth for that element, right? Do you guys understand what I mean? Mm-hmm. So if I have like mostly, let's say in our world, most of the carbon in our world is carbon-12, right? Most of it, most of the isotopes. But there are a few versions that have like carbon-14 and carbon-13 or whatever, right? So when I average those all together, what will I get? I'll get carbon like 12. I'll get 12 point something, a little higher than 12, right? Which just means that the most abundant isotope is 12, but there are a few that are a little higher than 12, right? So this number you always find where? Right on the periodic table underneath the thing, right? If I ask you for the mass number, can you just substitute this number for the mass number? No, why? Because this is an average of all of them, right? Whereas the mass number is only referring to one specific isotope of that element, right? So the atomic weight, atomic mass is usually a decimal place number, right? But what does it tell us about this? So if I ask you to look at calcium, right? And I say, okay, calcium, what's the most abundant isotope of calcium, do you think? Calcium 40, right? What about, let's see, what about for aluminum?
27.
Excuse me, 27, right? Excuse me. I thought I came to school today thinking like I was getting over a cold, but actually like I'm starting a cold. So I'm sorry if you guys all get it, but it's really important that we start this new lesson. So all right. Anyway, okay. So you guys understand what's going on with the mass number and atomic weight, right? Okay. I was gonna ask another question about that, but I don't think. Okay. So you can tell what the most abundant isotope is based on this thing. Okay. All right, so let's look at this table and just like marvel at it again. So how is it arranged again? So from left to right and from top to bottom, we're going in order of increasing protons or increasing atomic number, right? Oh, the thing I did want to ask you guys, if you look at like most of the atomic masses or the atomic weights, right? What do you notice about them? Like for example, like carbon, nitrogen, oxygen. Yeah, those three. What do you notice about like their atomic weight versus their George?
It's almost like always like double, so it's normally like 1 to 1.
1-to-1 ratio of what?
Of protons to neutrons.
Protons to neutrons, right? And that's what Charlie said, right? She said that like, neutrons and protons, but do they always have to equal each other? No, but usually they are, and that makes them more stable, right? One I want you to look at is hydrogen, right? Can everyone look at the atomic weight for hydrogen? What is it? It's 1.008. So what's the most common isotope of hydrogen? You have to round it to the closest whole number, so it's 2. I'm sorry, so it's 1, right? So hydrogen 1, that means how many protons are there? 1. How many neutrons are there? None. So the most common isotope of hydrogen actually has no neutrons, right? Can anything else have no neutrons here? It's basically only hydrogen that can have no neutrons in its nucleus, right? Okay. So how is it arranged? So it's arranged in increasing atomic number, right? And then it's also arranged in vertical, right? Do you see the vertical columns? Those are called families or groups. Huh?
Halogens. I know that one.
Good. Well, that was in the song too, right? and then, so they're vertical columns, families, or groups. And then horizontally, do you guys know what the horizontal ones are called? Periods, good. Arsh, do you want to teach this?
No, I'm good.
No?
No.
No, I think we're all. I want to see pizza.
He's pretty good. He knows it. Wait, where did you go to middle school again?
Marlboro.
Who else went to Marlboro here? So you guys all know this too. Huh? So you guys know this too. No, it's good to have people around the room that know. Okay. All right. So I want you guys to look at this, and I'm sorry again. This animation is so sad and really pathetic. But all right. So groups here, the groups and families, they're going where? Vertical, right? So they're the groups and families, right? So, and I want you, when we talk about the group and family names, I want you to go by the one that has the A after it, like the non-Roman numeral, like the one that has the A here. Like 1, 2, we're ignoring all these, and we're going 3, 4, 5, 6, 7, 8. Okay? And then, what are the ones that go across again called? Periods, right? So those are, it does not look awful. All right. All right, so do you notice how it, and I didn't realize I had done it, do you see how these are above that instead of underneath it? It's like a basket, right? It's so so the bottom part, so basically this part all goes, it's all in here.
It's almost like if you were to
So these are part of this period, and these are part of this period. But it's they just didn't fit nicely into this nice symmetric shape of it. So they kind of just be insert lanthanize and actinize here.
If you had a piece of paper, having it you cut these off and tape them on over here, and almost fold.
Oh, that's kind of cool. Or if you kind of fan them in and
almost, yeah.
Yeah, unfortunately we're not that advanced here. Okay. So we're good here so far? Okay. So now, and the organization actually really makes sense. So the period number, so that's this. So this would be period, 1. This would be period 2. This would be period 3, etc., etc., etc. We're not going to go beyond this really. But every time you have a new period, you're adding a new energy shell. So take a look at this. So here's hydrogen and here's helium, right? Those are the only 2 elements in this period. They have, so here's their nucleus. Let's pretend that, that's their nucleus. They have 1 energy shell surrounding their nucleus, right? Are we good? So then if the period number represents the number of energy shells, how many are these, all of them in this row going to have? 2 energy shells. So remember, it's going to look like that, right? The next one, period 3, what's it going to look like there? Right? So as you're going down, the period number corresponds with the number of energy shells that they have. Right? Pretty easy? All right? The group number, the ones that I underlined before, and I guess that slide is not aligned with this slide, so all my dashes are wrong. But so the group number means something too. So basically the group number means, so this is group 1, remember? We're going to just use the number before the A, right? So this is group 1, this is group 2, this is group 3, 4, 5, 6, 7, 8, right? The group number refers to the number, does anyone know what it is?
I'll take a guess. Isn't it the number of ions or not ions, the number of electrons in the shell?
Which shell?
The outer shell. It's I forget what it's called already.
The valence shell, right? Perfect. So it's the number of electrons in the outermost shell. So for hydrogen, let's look at hydrogen, right? Hydrogen, we know it has 1 energy shell, and how many electrons does it have? It'll have 1 in it, right? That's what it would look like, right? What about helium? Helium, we know it's still in period 1, so it has one energy level, right? How many electrons does it have, though?
8.
So this is the one exception. The first energy shell can only hold 2 electrons. So it has a full electron shell. So H has 2 electrons in it, right? Are you okay with that? This one is like really the only exception, okay? So the first energy shell can only hold 2 electrons, right? Okay, what about the next one? This one has how many energy shells?
2.
2, right? So how many electrons are going to be, and how many are going to be in its outermost shell? Because that's determined by the group number, right? So there's only going to be 1, so here's that one. And how many other electrons does it have? It still has 2 other ones, right? Where are they going to have gone? In this inner shell here. Right? Are you guys with me? Right? So in a neutral atom, remember, how do we determine the total number of electrons? So sodium, right? How do I know how many total electrons it has? George, you know? How many protons does it have?
11.
So how many electrons? If it's neutral, how many electrons is it going to have? It's going to have 11 too, right? So for sodium, let's try sodium, right? It has, how many energy shells does it have? 3, because it's in the 3rd period, right? And then how many electrons does it have total, we said? We have 11 to work with, right?
And you have 1 on the outer.
And how many do you have on the outer shell?
1.
1. How do we know that?
Because there's like the 2 and you have the 8.
Wait, no, wait.
It's in that group.
Because it's in this group, which has all of these only have how many electrons in their outer shell? 1. So I'm going to put that there. This is sodium, right? So I put that one there, and then how many do I have left to work with then?
10.
I have 10, right? How many go in the first energy shell? 2, and then how many would go in this one then? 8, right? Who said what?
Arya said 4, and I was confused. I'm confused as to how we got into the school.
Lidu, are you confused? Okay, so I can figure out the number of total electrons that I have by looking at the total number of protons. Right? So the atomic number is going to be equal to the same as the number of protons, and also the same number of electrons in a neutral atom. So if I'm saying sodium's neutral, and it has 11 protons, that means how many electrons does it have to have? 11, right? And I know that only 2 can fit in the first energy shell, right? And I know that in the outermost one, judging by the group number, I know that in the outermost shell, it's going to have only 1 because it's in group 1. So then I could deduce from putting the 1 out there and then the 2 in the innermost shell, which I know only houses 2 electrons. The rest of them, from that 11, right? From that 11, I took 1 and I put it on the outside because that was the group number. I took 2 and I put it on the inside one. So I have 10. Sorry, I had 10 here. Then I took 2 more and put them on the inside shell, so I had 8 more. And all those 8 would go in the second energy shell. Right? All right. So so the first energy shell holds 2 electrons, max, right? How many electrons can the subsequent energy shells hold? 8. That's the magic number for the subsequent ones, right? Are you guys okay? Have I lost you? You know, this chemistry is like, it's rough.
Everything except for the first innermost shell holds up to 8.
Mm-hmm.
Okay.
So basically, let's try another one. Let's just try another example, right? Let's do phosphorus, all right? Phosphorus. What group is it in? Well, I'm sorry. What period is it in? I'm sorry. 1, 2, 3. So it's in period 3. So here's the nucleus. Let's say how many electron energy levels is it going to have? 1, 2, 3. Right? Okay. And then what group is it? What group is it in?
5.
Group 5. So that means that 5 means how many? It means there are 5 electrons in the outermost shell, right? So let's put those 5 there, right? 1, 2, 3, 4, and then let's double up one of them, right? Okay. So how many total did phosphorus have if it was neutral to start? So I had 15 electrons to start because I had 15 protons, and we need 1 for 1 if it's going to be neutral. So I took those 5 from the valence shell, and I put them in the valence shell, right? So I have 10 left over, right? Where should I put these then? 2 in the first one, because that's the max that the first one can hold. And then I put 8 in that one, right? And so now I have a total of 15, right? And I know that there are 5 in the valence shell, right? Are you guys good? Do you want to try another one? Why don't you guys try doing oxygen? All right, and I'm going to have someone come up here and do it for me. Have Olivia do it. She's artistic. Art and artistic talent at all, but she'll make it. I'm not sure where to stop today. I'm trying to decide.
Yes.
Now? Too much like overload already?
No.
Wait, how much time do you have left in class?
So what I'm thinking this week, guys, is I'm thinking to get back on the Friday quiz schedule. So I'm thinking you're gonna have a quiz on Friday on chemistry. Are you all right with that?
Yes.
That means that we're gonna, have to move swiftly, but it means we're not gonna dwell on it, and we're gonna get into next week. We're gonna start carbohydrates, which is like real bio. I mean, this is bio, but so quiz on Friday, okay?
Wait, sign up for anything.
I signed up when I decided to come to this.
Yeah.
It
It doesn't matter. Because in reality, you never know where the electrons are ever. So it's always like moving around in waves and. Huh?
Nothing.
What happened?
I heard him say my name.
So like we were saying that like we're probably gonna drop out if this when this gets too annoying. We're gonna be like we're just gonna commit George because
My boy dropped me out, basically. See what he's saying.
so sad.
What's so sad?
I know.
He said he's dropping out, but he's still here.
He's a
So,
quitter.
like,
Who's dropping out?
George.
You're leaving the school.
Thank God.
What's your homeschool?
Middletown High School South.
Okay. So you went to
Yeah,
middle school with like
you're fine.
Jillian and Jordan,
Yeah.
but you don't like it here? No? Really? Do you play sports for your home high school? Yeah.
It's baseball.
What? Baseball? So
I gave him so much time.
has baseball season started yet?
Yeah.
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 So you just feel it's too far, or do you feel like it's?
It started in November.
For the practice, for like
I still need to be there every
Alright,
day.
you do calm
Why do
down.
you guys care?
Don't attack
I
her.
really feel.
Hey George, do what makes you happy.
You feel appreciated? That's yeah. You've like decided for sure, or like you're.
Yeah. I also don't want to go into this field anymore.
Oh, interesting. What what turned you off? Like, was it a class that you took like last?
No, it's not like. I don't know. No, it's not.
It was me.
I don't know. It's just like it seems not.
Not for you.
Me, yeah.
Fair enough. That's fair.
This is just an accident in combat. That's probably why.
But yeah, there. Yes. All right. Are we? It's what? I know it's almost over, so we're not going to do too much more. All right.
Sorry if I
No, it's perfect. You're fine.
All right. So what do you guys think? What do you think? So this is oxygen, right?
right now.
So oxygen, we have. So how many energy shells should we have? Two, right? And how many valence electrons should we have?
6.
6. Do we have 6 here? 1, 2, 3, 4, 5, 6.
Should they be in pairs?
They don't technically have to be, but
Oh.
sometimes they are drawn in pairs. So that's like conventionally they. Sometimes you might want to do that just because sometimes later we're gonna do something like this, where they do actually have to be in pairs, like around the Lewis dot structure. But for now you're fine. So we have 6 out here, we have 2 out here, we have total of 8 because 8 protons, 8 electrons. So we're good, right? So you guys could do this, and if I gave you like an element, you'd be able to. If I gave you this kind of diagram, you could tell me what element it is by figuring out how many electrons it has, right? And then you could figure out how many protons it has in a neutral atom, which would be the same. And then you could tell me which element it is, right?
Yeah.
Okay, good. Omar?
If we have to draw a diagram of oxygen,
Uh-huh.
we have to draw like 118.
Electrons, yeah. Yeah. But like the orbitals, like the different energy levels get a little more complicated. So we're not really gonna go below this level here. So don't worry about it, Sarah.
What does it mean when the atomic weight is in brackets?
I think that's because it's like those. Yeah, it's a solid number, and I think that's because like those are all man-made like isotopes. So it's not like they have like naturally occurring ones on Earth that they would measure or take an average of. So, good question. Arsh?
Once you start like losing and gaining electrons, wouldn't you be working with isotopes?
No. Once you
no, I know isotopes. Ions.
Yes.
All right.
And so if I gave you an ion, you'd know the charge of it, and then you'd know that the number of protons and electrons is not equal, right?
Yeah, because like, then you get cations and anions. Probably.
We'll get into that, but don't scare people. Yeah.
Sorry, I don't worry.
All right. Shh. All right. I want you guys to just do just a few more things, all right? Today, I promise. And then you guys can. Then we can relax. I'm going to give you a worksheet. I'll post a worksheet with just like practice questions from this. I didn't give you the questions today because I didn't want you just like filling them in. I want you to like think about it and like kind of take your own notes and then just fill them in as practice, right? So I'll give you a worksheet to do. And I also wasn't sure how far we were going to get, so that's another reason. Yes?
Is it assumed that everything like on this table is neutral?
Unless I do something like this. If you see it like that, and if I say draw like a Bohr atom structure for this, then that complicates things because it means that there's a plus charge. It means that there's one less electron than there should be. Right?
So like on the pretest, it had like calcium and with like
if it had
plus.
Calcium 2+, yeah. What is that? That means that it's not
more protons in there.
Yes, but you can't gain protons and still be calcium. So what had to have happened in order to get that +2 charge? You can't gain protons, you have to have given away electrons. So this means that it's lost 2 electrons. You get that right? Yes.
Is hydrogen neutral?
Hydrogen, so all of them are neutral unless they have the weird little so this hydrogen, if I gave you hydrogen like this and I said draw the Bohr model for this, you would just draw like that, right?
Okay.
But if I said draw the Bohr model for this, right? This is an ion, so then you would draw that. Because there's no electron there because it gave away its electron because it doesn't have any electrons.
Okay, but wait, why is the mass number equal to the atomic?
Because it has no what?
No
Neutrons.
Oh, okay.
Okay?
Yeah, that makes sense.
Electrons do not get considered in the masses at all because they're so light and minuscule compared to like the size of protons and neutrons.
Okay.
All right? Okay, so we're back to the periodic table and the beautiful organization. I want you guys to draw these sort of things on your periodic table. So basically, metals are on this side of the periodic table, in general on the left side, but I want to show you guys this staircase thing. And I want you to draw this in too. All right, do you see where I did that?
Oh, yeah.
All right, so anything to the left of the staircase is a metal. Okay? And then that means anything to the right of the staircase would be a... You're getting ahead of us.
Sorry.
If this is a metal, then those are non-metals, right? Again, I'm going to throw in an exception. What's the exception?
The metal.
No.
Why?
Hydrogen. Hydrogen is not a metal. So
Sorry. Okay.
So all these here, and then all these in here, those are all metals. Non-metals are all these over here plus hydrogen, right?
Wait.
We're just kind of ignoring these guys over here,
Wait,
but
so TS is or is not?
I mean, yeah, we could convince.
Tennessee.
You know, it's like a man-made compound, so I honestly don't even know.
Okay.
But let's just like ignore it. But I do want you to know that the staircase goes up till there, right? So polonium, antimony, germanium, aluminum, those are all technically considered metals, right? All these on the right side of the staircase, those are all technically considered non-metals. But as you'll learn, they're called metalloids. Thank you, Arsh. I wasn't going to get into this today. But anything like all of these touching the staircase up till here, like the blue ones, are all like they kind of act like metals sometimes. They kind of act like non-metals sometimes. So they're kind of like wishy-washy. Aluminum is clearly just a metal, though. Even though it's touching the staircase, it's still just a metal. But all those blue ones are metalloids.
So we're exempting all man-made stuff, like even to
I mean, I just don't, like, I don't really know that much about these new things, so I'm just ignoring them. All right? Okay, so you need to know that metals are on the left side and non-metals are on the right side. We're good with that? Okay, what do I have next? Okay, and then if you guys have like crayons, let's just go through the groups real quick. Okay, so do you guys remember? We're gonna go for it. Arch, thank you. He kind of pushed us over the threshold. We have to do it now. Why did I move hydrogen? Because I moved it over because I want you guys to like be able to group these the way they're supposed to be. I know. Well, they wanted it to look, because it behaves like a group 1 metal. That's why they put it over there, because it has one valence electron, and all of these have one valence electron too, right?
Why don't they draw the staircase like all the way over?
All the way over to there?
To where hydrogen is, the line that goes up.
Because it would still be on the metal side.
Okay.
All right, shh. All right, we need to get this done. We're almost done, I promise. Okay, in the song, shh. So not only do they have like names by their groups, like this is group 1, this is group 2, 3, 4, right? They also have like actual names. So do you guys remember the song? They said halogens, in like the chorus part, they said halogens react aggressively with alkali. So group 1 metals are also known as alkali metals. Right? Remember, left is metal, right is non-metal, right? Mike, are you with us? Left is what? Left is metals, right is non-metals, okay? Group 1 is called alkali metals, right? Group 2 is called alkaline earth metals. And how many valence electrons do alkaline earth metals have? 2. Okay? In their valence shell. Because their group number is 2. That's how many valence electrons they have. All right. The next group that they talked about in the song was what? Before the noble gases. The halogens. They said the halogens, which is group 7, it's all these. Right? They said that those react aggressively with alkali metals. The ones in group 8, those are the noble gases. Because they're so noble that they don't want to react with anyone. Okay? And then these right here, these kind of purple ones, the reason I moved hydrogen over here is because it belongs to this group of 6 elements which make up the majority, like over 96% of the human body, or like living things. So those are called, and the way to remember it is just schnapps. Right? And that's just the letters of the elements, the symbols, right? So carbon, hydrogen, nitrogen, oxygen, potassium? No. Phosphorus, and sulfur. All right? We're ignoring selenium. We kind of have to ignore some things just to make it like neat and clean for us to understand it as like first year bio students, right? Someday you guys will get into the beautiful intricacies of it, and you can teach me.
You guys should ignore me. I'm just letting you guys know.
All right. We have to get through 2 more groups, and then we're good. And then I'll let you guys go. Metalloids, right? So metalloids are the ones that are touching, they're blue, and they're touching that staircase, right? So if they're touching the staircase, they're a metalloid, except which one touches the staircase and is not a metalloid? It's clearly just a metal. Aluminum. That's why. So anything, do you see how boron's touching the staircase here? Yes. Right? It borders the staircase, so that's a metalloid. These 2 both touch the staircase. These 2, right? These 2. This one doesn't. It does, but it's not a metal. It's not a metalloid. It's a metal. Just, you guys know aluminum, right? Yeah. It's clearly a metal. There's no doubt about it. Okay. All these in here and down here, those are called transition metals. And we're not going to talk about them at all.
I'm glad.
But it's good for you to know that, right? Okay? transition metals, and these would be included in those. Sometimes they're called like the lanthanides and the actinides. Don't have to know that. Just know that that's like they would go right here, right? So what did we talk about today? We talked about the periodic table organization. We talked about numbers. Atomic number is what? The number of protons. Mass number is the number of protons and neutrons. How do we figure out the number of electrons in a neutral atom?
If it's neutral, that'll be the same as the atomic number.
It's the same as the atomic number. How do we find out the number of neutrons? Subtract the atomic number from the mass number. What's the mass weight or atomic weight?
The average of all the elements.
The average of all isotopes. You guys all know what an isotope is, right?
It's the element.
Okay. So preview. Can we change the number of protons and still be the same element? No. Can we change the number of neutrons and still be the same element?
Yes.
Yes. It would just be a different isotope. Can we change the number of electrons?
No.
We can.
Oh, we can. But let's
And then it becomes an ion. It's no longer. It's still an isotope because it has a certain number of neutrons, but it also becomes an ion, which means that it will have a plus or negative charge total, right? How did it get that plus or negative charge? Not by getting protons, because you can't get protons because then you'll change your element. You have to exchange your electrons. That's what makes the charges happen, right? Are you guys all with me? You guys did better than I thought. It was actually not as painful as I thought it would be.
I apologize for making you talk about 3 times worse.
For the pretest? It's okay. The lower the better.
I feel so
It's
dumb.
so wow. If you're anything that you learn at all, then it's like
Can you let us know what the latest grade on
I will, and I'll post them today. I'll make sure they don't count for real grades. But we get to know what our grades. You'll know what you got.
You're gonna put it as like any normal grade, and just like give it 100.
You guys, please bring. Oh wait, homework. Check classroom. I'm gonna post the worksheet, the first page of the worksheet. So please do that just to test yourself, and also make sure to keep your periodic table with you. Like bring it back. I have a few extra copies.